In the last video, I left you with the question, if f of x equals x squared, then what is f inverse of 4? So if we start to approach this the same way that we did the previous problems, we might say, well, what x value makes x squared equal to 4? And that's a perfectly good approach. And then you might say, okay, well, let's just take the square root of both sides. So if I take the square root of 4 and the square root of x squared, I get 2 equals x, right? But doesn't negative 2 also work? It does. There are two answers. So f inverse of 4 seems like it could be 2 or it could be negative 2. And we know that that's not a function if we have an input and we get two outputs, not a function. So how do we correct this issue? Before we get to that, let's just look at this example graphically. If our output is 4, then we want to know what the input is, what the x value is that gives us 4 for our y value. The graph clearly shows that there are two of those, negative 2 and 2. So if we were to draw a horizontal line at 4, it would hit the graph at two places because there are two inputs that give us 4 for an output. We're going to formalize this rule in just a minute, but what we're seeing here is that a function does not have an inverse if, let's get rid of this little window so you can read it. Okay, so a function does not have an inverse if a given if a given output can be obtained from more than one input. So what I mean is that there are two x values or more that give the same y value. So let's write that too. Two or more x values have the same y value. And graphically, this means that there are two x values that have the same height, in this case, we have negative 2 and 2 both have their y value equal to 4. So a horizontal line intersects the graph in more than one place. That's how we'll test for inverses graphically. So let's write that down. This is called the horizontal line test. Just like we had the vertical line test for functions, we have the horizontal line test for inverse functions. So function f has an inverse function if and only if no horizontal line intersects the graph of f at more than one point. So looking back at this one, it has no inverse function because there are lots of horizontal lines that I could draw that would intersect the graph at 2 points. So here are two examples that we can determine whether or not they have inverses by using the horizontal line test. This first one is the sine function. We'll see a lot of this during the second half of the year. Does this have an inverse? Well, if I draw a horizontal line, it intersects the graph in many places. So this function has no inverse, at least not the way that we've described it here. What about the function x cubed? Any horizontal line that I draw will intersect x cubed at only one place. So this does have an inverse. And in fact, we found it in the previous video. Its inverse is the cubed root of x. Because we saw that if you compose the cubed root of x with x cubed in either direction, you'll get x back. So this is a graphical way to determine whether or not a function has an inverse. We have an algebraic characterization of it too. Actually, we'll talk about the algebraic characterization in a second. I want to do one more thing with the graph. So is there a domain where x squared does have an inverse function? So if I restrict and only draw the graph for certain x values, is there a way that I can make horizontal lines intersect in only one place? So take a second to think about that. And I'll give you one solution. What if we just look at the positive values for x? So if we restrict to the positive, we call this restricting the domain. Restrict the domain to x greater than or equal to 0. Then the only part of the graph I'm looking at is this right-hand part. And now if I draw a horizontal line, I'm only going to intersect in one place because the left half of the graph we're not including anymore because we've restricted the domain to only positive x values. And in this case, we can figure out that f inverse of x is the square root of x because square rooting undoes x squared. So let's check this. If I do f of f inverse of x, then I'm doing f of the square root of x. When we take the square root, remember it's the principal square root, meaning it's just the positive. So when I plug a positive number into x, so I'm going to plug square root of x into the x squared function, I'm going to get x back. And because our domain was restricted, this x is positive, this x is positive. There's no ambiguity. Now if I do f inverse of f of x, then I'm going to do f inverse of x squared, which is to take the square root of x squared, and we know that we'll get x back, but x was positive in the first place, so there's no ambiguity after we've squared it that we'd get a positive thing. And then, so for example, if we plugged in -2, which we're not allowing, I would get f of -2 is 4, and f inverse of 4 is 2. So what I plugged in would not be the same as what I got out, but since I'm restricting to positives, I would never plug -2 in the first place. I'd only plug in something positive, and I would get that positive number back out after doing the composition. Okay, now let's talk about that algebraic characterization that I mentioned earlier. So here's a definition, which is basically just a more formal way to phrase the rule that we wrote down earlier. So a function only has an inverse, or does not have an inverse if 2 or more x values have the same y value. Here's another way of saying that. A function is called one-to-one if each value of the dependent variable y corresponds to exactly one value of the independent variable x. So this is saying the same thing. An output has exactly one input. You can't plug in -2 and 2 and get the same output. And a function has an inverse if and only if it's one-to-one. So if you can check that this is true, then you know the function has an inverse. So I want to keep looking at the x squared function. Let's look at the table here. And we'll be able to see from the table that it's not one-to-one, because here I have 2 x values, -1 and 1, that give me the same y value. They both give me an output of 1. If I were to try to draw a function table for f inverse, then my inputs, let's make them 4, 1, 0, 1, and 4. My inputs would be -2, -1, 0, 1, and 2. So here I have, that's f inverse of x. Here I have a problem. This isn't a function table. because the same input value of 4 gets mapped to 2 different output values. We know that this is not a function. Unless we restrict the domain and we don't allow these negatives. Okay, so we'll do some more examples in the next video of how to compute inverse functions, both graphically and algebraically. But I wanted to show you this careful example worked out in lots of detail so that you could see the cases where there is no inverse function unless you restrict the domain. So please come to me if you have any questions. This topic is a little bit more confusing than what we've seen so far.